So first is state vectors and linear operators. State vectors and linear operators, observables and quantum dynamics, simple harmonic oscillator, angular momentum, spin angular momentum, and these things. So this is unit 10, 11, 12, 13, 14. So quantum mechanics in Hilbert space. So let us go through this text. Is the screen visible? I think it is visible now. So go through this text. Then we'll start discussing what is state vectors and linear operators. Okay. So let us have this. And after you go through this 2 pages text, 1.5 page text, then we'll discuss it further. Please go through this.
Sir, you are not audible, sir.
Hello.
Dr. Sahu, you are not audible, sir.
So I think you have come across this, and in unit 13 and 14, these things. So basically, Hilbert space is a mathematical formulation which give a physical flavor, and physical concepts which can be explained in terms of things previously known can be better understood by using this concept. So is the screen visible?
Yes, sir.
So at the outset, I am very much grateful to the IGNU Bhubaneswar RC and Deputy Director Dr. S.K. Panigrai and Director Sir and all the participants who are present in this class. Okay. So I think Dr. Panigrai Sir is in the virtual room. Okay. So, you know, I was also in the Dr. Patra, S.K. Patra's sir's class, and they taught you advanced quantum mechanics 2, and they discussed very similar things which we will discuss today. That is in your semester 2. I think I am audible now.
Yes, sir.
Yes, sir.
Okay. So actually, a wave function psi can be expressed in terms of linear combination of a number of wave functions psi1 and psi2. And when we had discussed your wave packet in the previous class, you have seen how we can superpose a number of wave functions, waves represented by wave functions, and those are localized in a position, in a point in the free space, and give you a wave packet that represents a particle. So those things, superposition of a number of waves is nothing but linear combination of a number of waves. So see, your psi is equal to C1 psi1 plus C2 psi2. I shall also discuss it in detail in the next class, how linear combination of wave functions give you a new wave function. And the solution of the same wave function is represented by that psi. So this is a statement of superposition principle, which says that if you add two states of quantum system, you get another state of the same system. So suppose there is a quantum system representing a physical object, and it has two states. Then you can get another state of the same system by superposing these two wave functions representing these two states. This physical property demands that the mathematical equation governing quantum mechanics should be linear. So unless the mathematical equation is linear, you cannot express the physical property of that wave function, of that system of that different states of the quantum system. So you know ordinary vectors, how the algebra of ordinary vectors are there. That is a dot product, cross product, addition, subtraction, your parallelograms law, triangle law, so on and so forth. You can add two vectors to get another vectors, and you use triangle law or parallelogram law for the same, and also you can resolute it to different coordinates and add them together. This would suggest that it might be possible to look upon the state of quantum mechanical system as a vector of same kind. It may not be the kind of vectors you normally encounter in physics, but the state vector is very much important when you discuss quantum mechanics. In ordinary vectors, a set of numbers are there that describes a system. So these numbers are different components, and which is called the basis of, these are the basis of your choice. Suppose your R vector is xi cap plus yj cap plus zk cap. So it has two components, and x, y, z can be represented by three numbers, either 7, 8, 9, -5, 7, 12, like this. So the quantum state of a system as a vector in a vector space. So you should first be able to describe it as a collection of numbers in an appropriate basis. Consider a state of a quantum mechanical system described by the wave function psi at any instant of time. If we are to consider psi r cap as a vector, its component would be an infinite set of complex numbers. Are you getting it? Which would be the value of psi at all points of the configuration space. There are three types of space. One is
Sir, screen
configuration
is not
space.
visible, sir.
Not visible. मुझे दिखाई दे रहा है?
हाँ सर, आपको दिखाई दे रहा है,
It's
लेकिन
visible, sir.
you are visible,
Visible ना?
but screen is not.
Yes, it's visible.
विजिबल मैं आज दो स्क्रीन से बात कर रहा हूं. मेरा नाम पे आपको दो स्क्रीन आएगा. दूसरे स्क्रीन पे विजिबल हो रहा है, जहां से वॉइस आ रहा है वहां विजिबल नहीं होगा. आर यू गेटिंग इट?
Yes, sir. In one screen it is visible.
One screen it is visible, in the other screen I am audible.
That one is muted. Yes.
ठीक है, तो ये काम करते हैं, उसको स्क्रीन मोड्स अभी दिख रहा है. I think now it is more clear. Am I visible? Is the screen visible now?
सर दिख तो रहा है स्क्रीन पर.
ठीक है, ठीक है. नहीं, वो शायद कंफ्यूज
But
हो
that
जाएंगे.
cannot be enlarged.
इसको
Yes,
कर
it is
लेंगे,
visible.
क्या एनलार्ज कर लेंगे, जहां आपका इक्वेशन आएगा वहां एनलार्ज कर लेंगे. ठीक है,
Okay, sir. Okay. Thank you, sir.
अभी इक्वेशन वगैरह नहीं है ना, तो इसका जरूरत नहीं है. कल जैसे मैं एनलार्ज करके दिखा रहा था परसों, उस तरह से कर लेंगे जब जरूरत पड़ेगा. ठीक है, आपके पास मटेरियल है, यू कैन गो थ्रू द हार्ड कॉपी ऑफ द मटेरियल. ठीक है, बट दिस इज पेज नंबर 9. ओके.
But sir, some of us don't have, I think.
सो एक काम करते हैं, मैं इसको आपके ग्रुप में डाल देता हूँ.
Sir, I am not in any group. That's why I wanted to tell.
ओके, आपका
You can
नाम
download the PDF also. Link also available.
अगर
PDF.
नहीं है,
But, sir,
it
excuse
is
me,
not
sir, sorry
too
for the
short,
disturbance.
then
Sir,
then
sir,
then
Please
we
put
can.
your WhatsApp number in the group. I will add you up.
Okay,
Thank you.
excuse me, but sir, I am not in any groups. In which groups shall I add?
Please put your WhatsApp number in the text
message
text
box,
box. I
in
will
the
add up.
message box, in the message box.
Okay, okay, sir. Thank you, thank you.
Sir, you carry on, sir.
Am I audible? Am I
Yes,
audible?
sir.
Yes, sir. Yes, sir. Yes,
वो
sir.
23, 25 वाला ग्रुप जो था उसी में डाल दिया, वही ग्रुप है ना?
सर मुझे तो कुछ मैसेज नहीं मिला है, कुछ कोई भी ग्रुप में मैं नहीं हूँ.
अभी आपको ऐड कर देंगे, अभी आपको ऐड कर देंगे, ठीक है?
सब ऐड हो जाएगा
इसलिए
ये.
सर मुझे कुछ भी पता नहीं चल रहा था, इसलिए मैं सोच रही थी कि कब
ठीक है.
स्टार्ट होगा.
ये जो है इग्नू एमएससी फिजिक्स 20 ये वाला मैंने डाल दिया, ठीक है? 23 to 25.
Yes, sir. Yes, sir.
हाँ, तो उनको ऐड कर दीजिए और उसको दोबारा फॉरवर्ड कर दीजिए, ठीक है? ओके.
सर ये फोर्थ सेमेस्टर के लिए है तो
सुनिए
मतलब
सुनिए, मैं लिंक दे दिया
Yes,
हूँ,
sir.
आप ज्वाइन कर लीजिए उसमें. लिंक दे दे रहा हूँ, ज्वाइन कीजिए उसमें, वही ग्रुप में.
ठीक है, लेट अस
अभी
मूव ऑन.
लिंक दिया हूँ, देखिए, ज्वाइन कीजिए. उसी को दोबारा फिर छोड़ देना.
7978.
सर ये तो 23 25 बैच है, लेकिन हम मेरा तो 24 जनवरी बैच है. क्या सेम ग्रुप है?
कंटेंट एक है, कोई प्रॉब्लम नहीं है, आप रहिए, बाद में देख लीजिएगा. लेट द क्लास स्टार्ट. रिज्यूम.
ओके ओके
सबको ऐड कर देंगे, थोड़ा देर ही लगेगा लेकिन हो जाएगा सब. व्हाटएवर
Okay,
मटेरियल इज दैट दैट विल बी रीसेट, नो प्रॉब्लम.
ओके सर, थैंक यू थैंक यू.
So let us continue. So we can have a linear. Am I audible now?
Yes, sir.
So
Yes, sir.
we
Yes,
can
sir.
have a
Yes,
number
sir.
of wave functions that represents vector waves in some sense, and if we combine them, superpose these waves in a space, those are localized at a region, and that gives you wave packet, and that represents a particle. So this was the story. So a collection of numbers in an appropriate basis gives you a vector. So a wave function vector, that is psi, wave function that is psi, which is a function of r vector. Suppose the state of quantum mechanical system described by the wave function at any instant of time. If we were to consider psi as a vector, its component would be an infinite set of complex numbers, which would be the value of psi at all points in the configuration space. So previously we have also discussed that wave function both real and imaginary. हाँ विश्वमोहन जी बोलिए. म्यूट कीजिए जो सब डिस्टर्ब है, कहीं घूम रहे हैं या घर पे दूसरा काम कर रहे हैं. प्लीज म्यूट योरसेल्फ सो दैट अदर पीपल्स विल नॉट बी डिस्टर्ब. ओके, ठीक है. So previously we had also discussed that psi has two parts, one real part and one imaginary part, and it can be represented in an argand plane. So in its real part there is real number, and in its complex part I and some number that is represented by complex number, which would be the value of psi at all points in the configuration space. So if a space can be described completely by your space coordinates, that is x, y, z, or theta, phi, r, z, rho, theta, like these things, then it is called in configuration space. The configuration space is completely described by your position coordinates. Similarly, you have a phase space. You might have come across this term phase space, and in classical mechanics, Dr. Nayak might have taught you. So phase space has two parts. One part is represented by your position vectors or space vectors, x, y, z, r, theta, phi, so on and so forth. And others part can be represented by momentum vector. So your phase space is represented by positions and momentums. And last one is your state vector. So state vector or state space is represented by your position, momentum, and time. So there are three types of space. One is configuration space, one is momentum space, and another is state space. So in configuration space, your wave function psi can be represented by just some numbers, complex numbers. Since in quantum mechanics, we mostly deal with functions, a vector describing the state of a quantum system is most often an infinite dimensional entity. So you might have infinite dimensional space in configuration space. In your Cartesian coordinate system, there are three coordinates. There are three dimensions. Similarly, you might have infinite dimensions in a configuration space. You have x1, x2, x3, so on and so forth, xn, and so on and so forth. So while a quantum state can be described by an ordinary vector with three components, it is useful to describe a quantum state as a vector in complex vector space. So your wave function or a quantum state can be represented as a vector in a complex vector space. So we can say that in quantum mechanics, the state of a physical system is represented by a vector in a Hilbert space, which is a complex vector space with an inner product. Are you getting it? So in quantum mechanics, if the system is represented by a physical system is represented by a vector in a complex, having complex numbers and your unit vectors, then we can say that it can be represented by a vector in Hilbert space. And Hilbert space is a complex vector space. And in Hilbert space, you will come across inner product. This vector representing the quantum mechanical state of a physical system is called the state vector, and vector space is also known as state space of the system. We shall discuss the attributes of Hilbert space shortly, but before that, let us have Dirac notation. So PAM Dirac has used Dirac bracket notation to solve quantum mechanical problems, and this is very useful, and this is very robust technique to describe a quantum mechanical system. And in your Dirac notations, you come across two things. One is Kate vector or simply Kate, which is represented or denoted by the symbol I am showing in the screen. See, this is your See, this is your Dirac Kate vector. Is the screen visible? हाँ, ये जो देखो एक लाइन है, ग्रेटर साइन है. सो ये जो है इसके अंदर आप लिखेंगे साई, तो ये रिप्रेजेंटर होगा केट वेक्टर रिप्रेजेंटेशन ऑफ दैट साई. ठीक है, दिस इज डिराक नोटेशन. अब नीचे देखिए एक अल्फा को लिखा गया है, क्वांटम स्टेट अल्फा को लिखा गया है इसमें. आर यू गेटिंग इट? दिस वन अल्फा. ओके, so this alpha is a quantum state and represented in ket vector. Or ket. Similarly, there is another symbol that is called bra, that is placed in left hand side, and this ket is placed in right hand side. So together it is called bracket, B-R-A-C-E-T, bracket. So in the left hand side bra, in the right hand side ket, and this represents the wave functions in Hilbert space by Dirac notation. Okay. So see, here is discussion on Hilbert space. The set of all possible state vectors that describe a given quantum mechanical system form a complex vector space, which is called the Hilbert space, as we had discussed earlier, of the system, and is denoted by H. So if alpha or beta are any two elements of H, the sum of two elements alpha plus beta is equal to alpha plus beta. So alpha ket plus beta in ket will give you alpha plus beta in ket notation. Is also an element of H. H is a linear vector space defined over the set of all complex numbers capital C. The vector sum is cumulative and associative. Commutative and associative. So what is commutative? In the previous class we had discussed, when something is commutative, then the commutator brackets give you non-zero value, zero value. If it is not commutative, the commutator algebra or a commutator bracket will give you something different value. So we will discuss it in the next class. As you have all requested to have a detailed class on operators, in that class I will show you how commutative relations is encountered in operator algebra, in operator mechanism. And similarly associative, which you have also come across in your algebra class. So suppose alpha, beta and gamma are presented in three ket representation. Then ket alpha in ket plus beta in ket will give you beta in ket and alpha in ket. So alpha plus beta plus gamma similarly will be associative and will give you alpha plus beta plus gamma in ket representation. The product of the state vector alpha with a non-zero complex number C. So C in ket alpha is once again a vector of Hilbert space. So if a quantum mechanical state of a system is represented by alpha in ket, the same state can also be represented by C, which is in alpha in a ket state. So the physical information of the system contained in the state vector does not change if it is multiplied by a non-zero complex number A, B, C and the element alpha, beta in H. So A plus B, those two are, A plus B are two numbers or constants. When multiplied with alpha function in a ket representation will give you A alpha plus B alpha, shown in equation 10.1b. There exists a unique null vector such that for any vector alpha, null vector when added with alpha, then it will give alpha. For every element alpha, there is also an additive inverse minus alpha, so that A plus minus alpha plus minus alpha in ket representation will give you 0. With these properties, we can state the following things. First is a superposition or linear combination of two or more state vectors of the quantum system is also a state vector of quantum system and hence an element of the Hilbert space. So psi1, psi2, psi-n, all these things can be represented by Kate representation and are the states of a quantum system. Then their linear combination can be represented as summation I is equal to 1 to n ci psi I in Kate, as shown in your equation 10.1c, where C1, C2, so on and so forth, Cn are complex number, is a state of the quantum system and a vector in the Hilbert space of the system. This makes the Hilbert space a linear vector space. So we know that the dimension of a vector space is the largest possible number of linearly independent vectors we can find for the vector space. If there is no such largest number, then we say the vector space has an infinite dimension. Okay, so the vector space has an infinite dimension. A set of n linearly independent vectors, phi1, phi2, so on and so forth, phi-n, forms a complete basis for an n-dimensional Hilbert space. If every element psi of the vector space can be expressed uniquely as a linear combination of these states, then we can represent it as shown in figure 10.1d, where C1, C2, Cn are complex numbers. So the coefficients C1, C2, so on and so forth, Cn of the expansion of your psi, wave function psi, are the components of the state vector psi in the basis. Psi1, phi1, phi2, so on and so forth, phi-n. In a finite dimensional Hilbert space, the vector psi can be written as a column matrix, as shown in expression 10.1e. So in quantum mechanics, we use both finite and infinite dimensional vector space. So we have two different types of bases for Hilbert space. One is denumerable and other is non-denumerable. So a denumerable base of a Hilbert space means that the basis vectors are countable. That is to say the basis vectors can have one-to-one correspondence with the integers. And an example of a denumerable basis could be the energy eigenfunctions of a particle in a box, or the energy eigenfunction of a linear harmonic oscillator we will discuss in the next class. Typically, the ket 0 is used to denote the ground state of the system. This means that a non-denumerable basis vectors are not countable. The basis vectors are labeled with a continuous variable. So let us say z that ranges over minus infinite is smaller than z, smaller than infinite. Then a typical example of a continuous basis would be the eigenstates of the position or momentum operators for a free particle. While the space of wave function for a free particle is infinite dimension, for a spin half particle, you have two-dimensional vector space. So an example of spin half particle is your proton, so also electron, and also neutron, though the subatomic particles. So you have two-dimensional vector space for this type of spin half particles. Finite dimensional space most often appear in quantum mechanics as a model simplification of the actual system. However, one has to be careful while considering infinite dimensional space, because a summation of the kind summation I is equal to 1 to infinite ci phi I may not converge. So next your bra vector, which I was discussing, and both bra and ket together will give you bracket for operation of your quantum mechanics. See, this is your bra vector, and greater sign in the at the first, then a vertical line. So if you put alpha, beta, like some similar wave functions in it, then it will be represented by bra representation. The bra vector of alpha is alpha and so on in the screen. The bra vector for beta is equal to beta, as you seen. So for every ket, there is a bra vector, and that can be represented as shown in the screen. The bra vector for the sum of two ket vectors, alpha and beta, is the sum of the bra vectors for each. So alpha ket plus beta ket is equal to alpha bra plus beta in bra vector representation, direct representation. The bra vector for C alpha is C star alpha, where C is a complex number and C star is its complex conjugate. the bra and ket vectors both of a state vector are the transpose conjugates or adjoints of each other. So bra vector of a wave function is adjoint of the ket vector of that wave function. So when we write psi in a column vector in ket notation, then bra psi is a row vector which is adjoint of psi. We can see it in your screen. So the first one is C1, C2, Cn in column matrix. Okay, and this is psi when represented in a column matrix C1, C2, so on so forth, Cn. Then it is in column representation, and its adjoint is that is shown in your row representation, C1 star, C2 star, so on so forth, Cn star in row matrix. So when your bra vector is represented in a matrix, then the column, your ket vector is represented by the star notation in the row matrix. Okay. Thus, we have two distinct vector space: the vector space containing the ket vectors H and the dual space H star, which contains the bra vector. So, ket vector psi belongs to H, and bra vector psi belongs to H star, and which is represented in a row format, and your ket is represented in column format, which is seen in your equation 10.2. Now we can write psi dagger. ये जो क्रॉस वाला साइन है इसको डैगर बोला जाता है. So ket notation of psi, its dagger will be bra notation of psi. So dagger represents the adjoint. So यहाँ कोई क्रॉस वाला साइन होगा, इसको डैगर बोला जाता है, तो इसको हम adjoint बोलते हैं रेस्ट ऑफ द नोटेशन का. Every ket vector in the vector space has a bra vector in the dual space, which is its adjoint, and vice versa. If the basis in the space of ket vectors is phi 1, phi 2, so on so forth, phi n, the basis in the space of bra vector is phi 1, phi 2, so on so forth, phi n. Then your inner product. So what is inner product or scalar product for any two elements alpha and beta in ket notation of a vector space, denoted by symbol a bracket alpha beta. So your alpha in ket, beta in ket can be represented by a bracket alpha beta, which is a complex number C. So bracket, in bracket notation, alpha and beta is shown in the screen, and it is C, and the inner product has the following properties. So what are the properties? First, if you interchange the role of two vectors alpha and beta in the inner product, then alpha beta in bracket notation is equal to C, gives us the complex conjugate number C star. So your bracket in bracket notation beta alpha will be C star, and alpha beta in bracket notation will be beta alpha in bracket notation, and its complex conjugate, or you say your transpose, adjoint. So if alpha beta in bracket notation is 0, it means that either ket alpha or ket beta both are null vectors, or that alpha in ket notation and beta in ket notation are orthogonal vectors. The inner product obeys both distributive and associative properties. This is another property. Thus, for arbitrary complex number a comma b and element alpha, beta, and gamma in ket notation, you have bra alpha in ket a beta plus b gamma will give you a in bracket alpha beta plus b in bracket alpha gamma, which is shown in equation 10.3b of your course material, study material. And another property, very important property, is the inner product of a state vector with itself is a real number. So since in bracket notation alpha is equal to adjoint of that alpha in bracket notation, we further impose the following condition on alpha in ket notation or ket vector, that is bracket alpha comma alpha greater or equal to 0. So this implies that the state vector alpha in ket is the null vector 0 in ket of the Hilbert space. The norm or length of a state vector is the quantity root over of bracket in bracket alpha, which is a real number. A physically acceptable quantum state psi in Ket notation has unit length. So in bracket psi is equal to 1. In quantum mechanics, we can interpret the inner product of two state vectors alpha and psi in a bracket notation alpha psi as a measure of the overlap between states alpha and psi, or the transition amplitude from state psi to state alpha, or the probability amplitude. So probability amplitude is represented by this. So the probability of observing a system in a state alpha in Ket notation, given that it is in a state psi, that is in bracket alpha psi square. So if your wave function is in bracket notation, then the formula of calculating the probability of finding that particle or that wave packet in a localized space will be bracket in bracket alpha psi modulus of that quantity and the square of that quantity. In quantum mechanics, it is usually convenient to work with an orthonormal basis. An orthonormal basis from any arbitrary basis which has no special properties whatsoever. We do this by a method you have studied, Gram-skimmed orthogonalization process. I have shown you in your mathematical physics class, second class. So an orthonormal basis, phi 1, phi 2, so on, so forth, phi n has the following property. In bracket, phi I, phi j is equal to del ij, that is Kroneker's delta, and its value will depend upon I and j. If they are same, then it has some value, and if it is different, it has some other values, and the two possible values are 0 and 1. So alpha C, so in C in your equation 10.3e, alpha is represented in a column matrix as it is a Ket representation, and bra is represented in a transpose of that values in a row matrix. So beta will be B1, B2, and so on and so forth, Bn in a column matrix. So the inner product is alpha beta in bracket will be A1 star B1, A2 star B2, so on and so forth, An star Bn, which can be represented as I is equal to 1 to n Ai star Bi. So Hilbert space is a finite or infinite dimensional linear vector space with an inner product defined on capital C. So then your linear operators in Hilbert space. So you know, linear operator is an instruction or mapping that transforms a vector psi of the Hilbert space H to another vector psi dash of H as follows. So about O cap, that is an linear operator, O cap psi is equal to O cap psi in Ket, that is equal to in Ket your psi dash. So your O cap denotes the linear operator. We use the same notation for linear operator that we have for quantum mechanical operator, and for arbitrary complex number a comma b and elements alpha and beta in Ket notation of your H, your O cap A alpha plus B beta is equal to A O cap alpha plus B O cap beta. For any two linear operators O cap and Q cap and a vector alpha, we define the sum of the linear operators as O cap plus Q cap alpha is equal to O cap alpha plus Q cap alpha. For any two linear operators O cap and Q cap and a vector alpha, we define the product of the linear operators as O cap Q cap alpha is equal to O cap Q cap alpha in bracket. An operator O cap is called the null operator if for any vector alpha your O cap alpha is equal to 0. Then an operator O cap is the unit or identity operator I cap if for any vector alpha I cap alpha is equal to alpha. If its value will be 0, then it is null operator. If after operating it, the value will be the same as that of the original vector, then it is called identity operator. So there is another operator that is inverse. So given an operator which acts as your O cap psi is equal to O cap psi is equal to psi dash in cat notation, we can define the inverse O cap inverse of the operator O cap as O cap inverse psi star is equal to psi in cat notation. And further, your O cap inverse psi is equal to O cap psi. So your O cap inverse psi dash is equal to psi dash. Since it is true for any cat, we get O cap inverse is equal to I cap. In general, the product of two operators is not commutative. So for any two linear operators, O cap and Q cap and a vector alpha will be O cap Q cap alpha is not equal to Q cap O cap alpha. So O cap Q cap is not equal to Q cap O cap. The commutator between the two operators is in commutator in the bracket Q cap O cap Q cap in bracket is equal to O cap Q cap minus Q cap O cap. So anti-commutator of two operators O cap Q cap can be written as O cap Q cap in curly bracket is equal to O cap Q cap plus Q cap O cap. While the brackets represent the commutator, your square bracket represents commutator, the curly bracket represents an anti-commutator. The product of any two operators O cap Q cap can be written as O cap Q cap is equal to half O cap Q cap plus half Q cap O cap. In the space of bra vectors, the operator is represented by its adjoint as shown in expression 10.8. This defines the adjoint of an operator, and if an operator O cap turns a ket vector psi into a ket vector psi dash, the adjoint operator O cap plus turns the associated bra vector psi into the bra vector psi dash. So next is your projection operator. For any two vectors alpha and beta of H, we define a formal product operator alpha ket and beta bra. The action of this operator on an arbitrary state psi, as shown in figure 10, equation 10.9a, will be in 10.9b. So this operator on an state psi is a new state which is parallel to alpha and has a magnitude which is the inner product alpha beta psi in the bracket format. So this format is called projection operator, and we denote it P cap alpha. This is projection operator. Okay. For a so projection operator has in the ket notation in a left hand side and bra notation in the right hand side. For a complete set of orthonormal basis phi 1, phi 2, so on and so forth, phi n, any vector psi in that space can be expressed as bra of psi, ket of psi is equal to summation I is equal to 1 to n ci phi I. And taking the inner product phi j and psi, the wave function we get the bracket format as cj or I is equal to 1 to n ci del ij, and you know the value of del ij will be either 0 or 1. So components of cj of the vector psi just phi j psi. So using the previous equation, you have psi in ket notation will be summation I is equal to 1 to n phi I psi, where phi I will be this notation, projector operator notation, pi cap. And this is an identity operator. So the projection operator projects a state psi to another state phi I with a probability phi I psi square. So your matrix representation of linear operators. So when you write down the linear operator in matrix representation, then by using matrix algebra, you can solve the quantum mechanical problem with effectively and accurately. In an n-dimensional Hilbert space with an orthonormal basis phi 1, phi 2, so on and so forth, phi n, a state vector is represented by a set of n components in that basis, and a linear operator by a set of n square components which form an n cross n matrix. So from equation 10.1c, we get psi dash is equal to O cap psi. So O cap summation j is equal to 1 to n Cj phi j, which can be represented as j from 1 to n Cj Oj phi j. So the writing phi dash in this notation in the same orthonormal basis, we can determine ith component of psi star psi dash as Ci dash is equal to phi I psi dash. So O is an n cross n matrix representing n by n matrix corresponding to the operator O cap in the bases phi 1, phi 2, so on and so forth, phi n. So the elements of O are Oij is equal to phi I, O cap, phi j. So the equation for the action of an operator on a state vector in a Hilbert space with an orthonormal basis phi 1, phi 2, so on and so forth, phi n, leading to another state vector psi dash is equal to O cap psi, and that can be written as a matrix equation as shown in equation 10.18. So your column matrix, जो आप कॉलम मैट्रिक्स आप किसको रिप्रेजेंट करते हैं, केट को. सो इफ केट इज रिप्रेजेंटेड इन ए कॉलम मैट्रिक्स C1 dash, C2 dash, so on so forth, Ci dash, so on so forth, Cn dash, then the matrix equation representing that ket that wave function in ket notation or ket vector will be O11, O12, so on so forth, O1j, so on so forth, O1n, O21, O22, so on so forth, O2j, so on so forth, O2n, so on so forth, OI1, OI1, I2, so on so forth, OIJ, so on so forth, OIN, so on so forth, ON1, ON2, so on so forth, ONJ, so on so forth, ONN. Okay, so there is a printing mistake in your material. You just spell it O12. First is O11 and the next is 1 O12. Please correct it in your material. And next column matrix will be C1, C2, so on so forth, Cj, so on so forth, Cn, as shown in the screen. So we have an n cross n matrix or n by n matrix O corresponding to the operator O cap. The elements of the matrix are O11, O12, and so on. And these are represented by bracket notation as defined in equation 10.17. The same matrix acting to the left on the row vector gives the row vector psi double dash is equal to psi O cap. We can write down the matrix representation of the product of two operators O cap and Q cap in the same way as shown in equation 10.19. Okay, so this is dagger O dagger Ij is equal to O star Ij. Now we are well acquainted with the rules for creating the adjoint of vectors and operators separately. So we have alpha beta dagger is equal to beta alpha, C O cap dagger is equal to C star O cap dagger, alpha O cap beta dagger is equal to beta O cap dagger alpha, as shown in equation 10.23a, 23b, and 23c. Then Hermitian and unitary operators. A self-adjoint operator O cap has the following property. O cap dagger is equal to O cap as expressed in equation 10.24. In bounded finite space, a self-adjoint operator is also Hermitian. In physics, Hermitian is the more commonly used term, and we shall go with this terminology. An anti-Hermitian operator O cap is defined as O cap dagger is equal to minus O cap. In the previous quantum mechanics class, maybe day before yesterday, I have described how you can say that an wave function is obey Hermitian property, and only when a wave function can be represented by a Hermitian operator and it obeys the Hermiticity, then only it can be physically reliable, and it can be physically possible. You can have a physical meaning of that wave function or of that expression. So O cap dagger is equal to minus O cap. The operator O cap can be written as O cap is equal to half O cap plus O cap dagger plus half O cap minus O cap dagger, which is the sum of Hermitian operator half O cap plus O cap dagger, and an anti-Hermitian operator half O cap minus O cap dagger. Observables in quantum mechanics are represented by Hermitian operator, as I have told you day before yesterday. So unless the Hermitian operator is not used, and we cannot say that whether that quantity is observable or not. If Hermiticity obeys, then we can say definitely say that it is an observable quantity. Because Hermitian operator, when we operate upon a wave function and give real expectation value, then we can say that it is an observable. Next is your unitary operator U cap, and is defined by the condition U cap dagger is equal to I cap. So U cap inverse is equal to U cap dagger, and your U cap dagger U cap is equal to I. That is unitary vector. Then your eigenvalues and eigenvectors, we have already discussed it in the previous class. So A cap psi is equal to A multiplied by psi. So your wave function psi, when operated by a vector, and it will give a number A with that wave function psi, and then your psi is called an eigenket or eigenstate or eigenvector. And that A, which is a real number, which is a number somehow, is called the eigenvalue of that wave function, and it represents the value of that physical quantity under discussion. Are you getting it? अब जब A कैप हम साई पर ऑपरेट करेंगे तो एक समथिंग आएगा 15, 20, 25 एक एक्सप्रेशन आएगा x स्क्वायर y स्क्वायर और e⁻x, एंड उसके साथ तो पुराना वेव फंक्शन साई वाला भी आएगा. सो साई को छोड़ के राइट हैंड साइड में जो बाकी टर्म आया उसको हम बोलते हैं आइजन वैल्यू, एंड दैट गिव्स ए सेंस, and it make us to feel that is the value of that wave function. Suppose psi is a position, suppose A cap is a position operator, then that A will be position eigenvalue. If A cap is an energy operator, then your A in equation 10.28 will be the energy eigenvalue. So we'll see how these energy eigenvalues can be evaluated by different physical situations, say simple harmonic oscillator, hydrogen atom, particle in a box, or particle in a three-dimensional well. Okay. Then there are more than one eigenkets corresponding to an eigenvalue A. Then these eigenkets are degenerate. Eigenkets of A cap with same eigenvalue A. If there is just one eigenket corresponding to this eigenvalue, then it is a non-degenerate eigenket of A cap. The set of all eigenvalues of an operator are called eigenvalue spectrum of that operator. So we'll have eigenvalue spectrum in case of your harmonic oscillator and hydrogen atom, and we'll see how we can get non-degenerate states and degenerate states in different physical situations, physical problems. Then equation 10.29 is an characteristics equation, and assuming that the inverse of the operator A cap minus A I cap exists, the equation gets transformed into psi is equal to A cap A I cap inverse 0 null vector, that is 10.30. So it is not actually correct. So in an equation is an eigenvector only if it is non-zero. If then the equation is always valid, but such trivial vectors are not eigenvectors always. Then your eigenvalues of Hermitian operator. And in equation 10.32, you can see omega vector psi n in ket, you will be omega n psi n. Then taking the inner product, as shown in figure 10, equation 10.33, you can have your psi n omega cap psi n is equal to omega n star psi n. Equating the right hand sides of equation 33 and 35, we get that omega n minus omega star n is equal to 0. So the eigenvalues of Hermitian operator are real. Hence, it represents an observable because it is real. Then eigenvectors of Hermitian operator. For a Hermitian operator, the eigenvectors corresponding to distinct eigenvalues are necessarily orthogonal. So if you consider a Hermitian operator omega cap acting on any two of its eigenvectors, psi n and psi m with distinct eigenvalues omega n, omega m respectively, where your omega n is not equal to omega m, then you can have these omega cap psi n is equal to omega n psi n. And now by taking the inner product, you can have your expression psi m omega cap psi n is equal to omega m star omega m psi n is equal to omega m psi n if your omega cap will be equal to omega cap dagger. Therefore, the eigenvectors are orthogonal and they can be rescaled to made orthonormal. So eigenvectors labeled with a eigenvalues omega 1, omega 2, so n omega n can be represented by orthonormal eigenvectors of Hermitian operator omega cap as shown in your expression 10.42. The eigenvectors of a Hermitian operator can be chosen to be mutually orthogonal and they form a complete set. And these are some problems. Then your eigenvectors of commutating operators. So you know what is a commutating operation, and from that your eigenvalues and eigenvectors of unitary operators are also derived. The eigenvalues are complex numbers of unit modulus. Eigenvectors belonging to non-degenerate eigenvalues are orthogonal. So unitary operators and transformation basis. So if orthonormal eigenvectors of Hermitian operator omega cap is an n-dimensional Hilbert space psi 1, psi 2, so on so forth psi n, and we have another orthonormal basis xi 1, xi 2, so on so forth xi n, which are not eigenvectors of omega cap, then matrix corresponding to omega cap in the basis xi 1, psi 1, psi 2, psi n is a diagonal matrix, and we can read of eigenvalues of the operator omega cap as its diagonal elements. Given any two arbitrary sets of vectors psi 1, psi 2, psi n and psi 1, psi 2, so on so forth psi n, which are both orthonormal and complete, and there exists an operator u cap such that psi I is equal to u cap psi I, then u cap is a unitary operator. So this is the algebra of unitary operator. Then your infinite dimensional Hilbert space. In an infinite dimensional Hilbert space, we have a non-denumerable basis, which we have defined earlier. The basis states will be represented by a continuous variable from minus infinite smaller than z, smaller than infinite. And if we allow the number of points n in the interval to be infinite, so that the function is defined at every point in the interval, then we have a natural generalization of the inner product in its infinite dimensional vector space as an integral. Fg in bracket will be summation I is equal to 1 to n phi gi, which is nothing but integration 0 to 5 fx gx dx. So these are the derivation. You can go through it. And if have any doubt, please ask. Then there are some relations, orthonormality, omega I, omega j is equal to del ij, where del ij is Kroneker's delta, and its value is either 0 or 1. And it is replaced with a Dirac delta function delta a minus a dash. So the completeness, your omega I will be I cap, which is equal to integration dA a I cap is equal to I cap. So your state vector can be represented by psi is equal to integration dA a psi. And the probability distribution we have discussed, that is nothing but summation I in bracket omega I psi square is equal to 1, or in integration dA a psi square is equal to 1. So this is the summary. There are some terminal questions in your study material and also the solutions. You may go through it, and you have any doubt, please ask in the next class. Then your next part of our discussion will be observables and quantum dynamics. So in the first unit, we have discussed how a Hermitian operator is very much effective and robust to let you know which quantities are observable and which are not. Now here we'll discuss some some more examples of observable quantities in Heisenberg picture. We have a Dirac bracket notation. And operator mechanism is one of the very important operation in your quantum mechanics so far as your matrix algebra is concerned. So the postulate one is every observable of a physical system is described by an operator that acts on the Kate vectors that describe the system, as we have discussed now. And postulate two is if A is the observable corresponding to the operator A cap, then the result of the measurement of the observable A for the physical system can only be one of the eigenvalues of A cap. And the postulate three is when a measurement of an observable A is made on a normalized state psi, the probability of obtaining an eigenvalue AI is given by the square of the inner product of psi with the eigenstate phi I of A cap, assuming that the eigenstates form an orthonormal basis. And we must not confuse between expectation value and eigenvalue. The expectation value is an average value, which I have discussed in your first class. And your eigenvalue is and expectation average value or expectation value can be a real value in the range of the eigenvalues A cap. The result of a single measurement is one of the eigenvalues. Average value is a average measurement, but eigenvalues are maybe the single measurements of any physical system. So it may have a single definite value, and it is one of the entire spectrum of the values. And the postulate 4 is the von Neumann measurement postulate. It states that if on measuring A for a system in a generic state psi, a result AI is obtained, then the state of the system immediately after the measurement is phi I. And your this type of vector, this type of measurement is makes the system state vector to collapse. So collapse to one of the eigenstate of the eigenbases are shown pictorially in expression 11.5. Psi is equal to summation I is equal to 1 to n ci phi I, and after measurement it will be phi I. So pictorially it is shown in figure 11.1, measurement of A. Then it has four represents four eigenstates phi I, phi 2, phi I, phi 2, phi n. And the outcome of the measurement will be A1, A2, AI, so on and so forth, AN. So these are the eigenvalues, A1, A2, AI, AN. And the states are phi 1, phi 2, phi I, so on, phi n. So we may conclude that the eigenstates of an observable form a complete state, and in quantum mechanical observable must be a Hermitian operator which has a complete set of eigenstates. Next is compatible and incompatible observables. So what is compatible? If the operator A cap and B cap commute, then the commutator on commutation this gives 0, and it is incompatible when A cap B cap do not commute. So we'll discuss in detail commutator algebra in your next class. If your A and B are compatible observables, the operators A cap and B cap commute, and therefore the operators A cap and B cap have a common set of eigenvectors. For non-degenerate eigenvalues, any eigenvector phi I of the operator A cap with an eigenvalue AI is also a simultaneous eigenvector of the operator B cap with an eigenvalue say Bi. So if the measurement of B is carried out immediately after the measurement of A, we would get the value Bi, and the system will continue to be in the state phi I. So pictorially it is shown here, measurement of compatible observable A and B in figure 11.2. And in figure 11.3, measurement of incompatible observable A and B are shown. Then your uncertainty principle, which we have discussed in your first class. So given an operator A cap, we define another operator del A cap is equal to A cap minus your expectation value of A cap or average value of A cap. So this is in your Dirac notation, your uncertainty principle. And these are the steps you should follow to arrive at the final expression. And these are the commutator algebra. I shall show you in the next class, which is in your unit block 2. The uncertainty principle derived is much more general because it relates the product of the mean square deviation of any pair of Hermitian operator. And these are following consequences for any two compatible observables A and B. Del A, del B greater or equal to 0. Therefore, A and B can be simultaneously measured with arbitrary precision. There is no restriction on the accuracy of simultaneous measurements. For any two incompatible observables A and B, del A, del B must always be greater than or equal to a positive definite quantity. So inherently, there is a limit to the accuracy with which A and B can be simultaneously measured. Thus, for every pair of incompatible observables, we have a Heisenberg-like uncertainty principle. Now, in your first lecture, you have seen, and I have shown in my class note, the time evolution of a quantum system. And this is described by time-dependent Schrodinger equation, which is there in your block 1 course material and also in my study material, which I have shown you in the first class. Then your Schrodinger picture and Heisenberg picture. But this is very important. Please be attentive. Let us suppose that we know the initial state of a system, psi t is equal to 0 is equal to psi 0. In that case, using Schrodinger equation, we can uniquely determine the quantum dynamics of the system. If the Hamiltonian operator of the system does not have an explicit time dependence, which also means that the operators x cap and p cap do not have a time dependence either, then only the state vectors are evolving with time. This is called Schrodinger picture of quantum dynamics. And you can express it in a time evolution operator psi t is equal to u cap t psi 0 as shown in equation 11.32. We can also write the corresponding bra vector psi t is equal to psi 0 u cap t dagger. Now let us derive the expression for u cap t in terms of eigenkets of the Hamiltonian operator. So you see in equation 11.34, psi t in ket notation will be summation I is equal to 1 to n ei psi t ei is equal to summation I is equal to 1 to n ait ei, where ait is equal to ei psi t are the components of the state vectors at time t in the basis ei. Now multiplying both sides and taking the LHS of this equation to 0, you can have I h cross del ai, which is a function of t with respect to del t, minus ei ai, which is a function of t is equal to 0. So you have ait is equal to ai 0 e to the power minus I ei t by h cross, where ai 0 is equal to ei psi 0 in bracket notation. So we know how the components of the state vector change with time. So by work out this, and you can have the final expression h cap e is equal to ee, and at time t, the state of the system is et in ket notation will be e to the power minus iet by h cross e in ket notation. The expectation value of an observable A at any instance of time for a general state psi of the system can be written in the form as shown in equation 11.48. When psi is a stationary state E of the system, then A cap can be represented as shown in equation 11.49, which is independent of time. So the expectation value of any observable capital A with respect to an energy eigenstate remains constant with time. This is also why an energy eigenstate of a physical system is called a stationary state of the system. This is also another way of describing the evolution of a system, which is called Heisenberg picture. So there are two pictures, Schrodinger picture and Heisenberg picture. So the Heisenberg picture goes like this. In this picture, the evolution of a system, we do not study the time evolution of state vector, but rather we look at the time evolution of the operators, which represents the physical observables of the system. So in Schrodinger picture, we see the time evolution of state vector. In Heisenberg picture, we see the time evolution of the operator that operated upon the wave function. That is actually observed in the experiments, how the different observables change with time. And this is the operator formalism in this picture. And we assume to evolve with time according to rule A cap H T is equal to U cap dagger, which is a function of T, A cap U cap, which is a function of T. So the derivation goes like this, and you have the final expression del A cap del T H is equal to U cap, which is a function of T dagger, del A cap del T U cap T. This is the Heisenberg equation of motion for Heisenberg operator A cap H. If the Schrodinger operator A cap does not depend explicitly on time, then del A cap by del T is equal to 0. And the equation will reduce to IH cross del by del T A cap H is equal to A cap H H cap H. And you can see that equation 11.61 and your Schrodinger in Schrodinger picture last equation, they show the equivalence of two pictures of quantum dynamics, which is keeping with the fundamental truth that the dynamics of the system cannot change with description. In Schrodinger picture, the state vectors have the time dependence, whereas the operators does not. In Heisenberg picture, the state vectors does not change with time, but the operators changes with time. It has time dependence. Then your Heisenberg equation for simple harmonic oscillator. Then the choice of basis, you can have it. Because in your Heisenberg equation for simple harmonic oscillator, H cap is equal to P cap square by twice m half m omega square X cap square. So by writing it in Dirac notation, you can have the solution. And here are some worked out examples and solution of those examples given in your course material. Then your simple harmonic oscillator 2. So we will discuss in the next class Schrodinger equation for simple harmonic oscillator and determine explicitly the eigenvalues and eigenfunctions. Here we'll discuss how we can solve it by using matrix algebra. And this is shown in your screen. I am showing here. And see, in the first class we are discussing 0-point energy. So see here the minimum eigen energy will be E. So your equation 12.14. E minus h cross omega by 2 is greater or equal to 0. So E is greater or equal to h cross omega by 2. It is non-zero. And it has a finite value and is greater or equal to h cross omega by 2. So the minimum possible value of eigen energy of a linear harmonic oscillator is h cross omega by 2. So minimum energy is h cross omega by 2 and the other values are greater than h cross omega by 2. So in classical mechanics, when your temperature will be 0 in absolute scale, so it is 0 Kelvin. So at 0 Kelvin, the particles stops oscillating. They have no vibration or they have no vibrational motion. But in quantum mechanics, even at 0 K, there is some oscillation and hence its energy will be h cross omega by 2. So at point 0 in Kelvin scale, there is a finite value of energy, eigenvalue or finite value of energy for the harmonic oscillator and it is h cross omega by 2. So the energy of harmonic oscillator at 0 K or at ground state will be non-zero and it is called 0-point energy. Somebody was asking in the previous class. Then expectation value of the Hamiltonian operator. So this goes like this: H cap is equal to something that shown in equation 12.17. So if X cap and P cap are Hermitian, you can work out and you can have the final expression H cap is equal to 1 by 2m P in bracket plus half m omega square Q in bracket is greater or equal to 0. So the expectation value of energy of a simple harmonic oscillator is non-negative. It is 0 or positive. Then your energy eigenvalues, and you can work out, solve it in Dirac bracket notation, and you have an infinite number of eigenvalues. And the simple harmonic oscillator can be written as a simple superposition of eigenkets of H cap, and your psi is equal to summation n is equal to 0 to infinite Cn n ket notation, as shown in equation 12.36. Then time evolution of state vector. You can see your psi t is expressed in the form of 12.38. Then creation and annihilation operator. Using the notation, we can have E in ket notation will be n in ket notation, and we can write H cap A cap n is equal to n minus half H cross omega A cap n. So similarly, your H cap n minus 1 is equal to E n H cross omega n minus 1 in ket notation. So the operator A cap is therefore called a lowering operator, as the action of the operator A cap on an energy eigenstate n is to turn the state into another energy eigenstate which has a lower energy n minus 1. Since H cap n minus 1 is equal to E n minus H cross omega n minus 1, then so the energy is reduced by 1 quantum H cross omega. So we can say that A cap effectively annihilate 1 quantum of energy, or 1 quanta of energy. This is why it is called annihilation operator. Similarly, your A cap dagger n is equal to root over of n plus 1. So see here, A cap dagger is called raising operator. It raises the value, increases the value with H cross omega. The action of A cap dagger on an energy eigenkette n is to turn it into another eigenkette which has higher energy n plus 1. Okay. Since energy increased by 1 quantum H cross omega, we can say A cap dagger effectively create 1 quantum of energy. Hence, A cap dagger is also called creation operator. Then your number operator. We define A dagger, A cap dagger, A cap as the number operator n cap, as shown in expression 12.49. And for two eigenkettes M and L, we get M n cap I L is equal to M delta ML, where delta ML is your Kroneker's delta. Then eigenfunctions of the simple harmonic oscillator. And you see your n in ket notation will be 1 by root over of n factorial A cap dagger to the power n O, or 0, null vector. Okay, and the wave function is psi1x is equal to A by 2 root over pi to the power half 2 xi exponential minus xi square by 2, where psi1 is can be written in terms of 12.67. Then your on-centric product del x is equal to root over of x cap square minus x cap expectation value and its whole square. And this uncertainty product you can see in your expression 12.75, 76, 77, and before that. So there are terminal questions, solutions and answers of this chapter. Then your angular momentum. And you can have raising and lowering operator, eigenvalues of L square cap, LZ cap, then angular momentum operator J cap, by calculating C plus and C minus matrix element for J is equal to half, so on and so forth. We'll discuss it in the next class. I think will be better for you. Okay.
Okay.
And then your spin angular momentum, and that will be also discussed in the next class. And we will discuss also your operator formalism, and that is very important. And we have discussed it in the first class. And as you have requested me in the first class, I shall also have a discussion support of. Please mute, Sachin ji. And after that, we'll have some examples. Your how can you solve your one particle in a box, particle in a infinite well, simple harmonic oscillator, and your hydrogen atom. And these will be in the next class. We'll discuss in detail. And I think which will be good for you by going through your text, your material, IGNU material or my note. In the first class, I have basically focused on my note, and this class on your material. Complete idea.
Both.
तो ठीक है, नेक्स्ट क्लास हम क्या करेंगे, हमारे नोट से पढ़ाएंगे, और बाकी यू कैन गो थ्रू द मटेरियल बिफोर दैट, so that you will have a better understanding. Okay.
Okay, sir.
So in the next class, I shall focus on my note basically, and after that your IGNU material. ठीक है.
ठीक है, sir.
Thank you for your patience hearing.
Thank you, sir.
Okay, sir.
Is slide visible?
Yes, sir, visible.
Okay. Shall we start?
Yes, sir.
Okay.
Yes, sir.
So today first we discuss about the virial theorem, a very important theorem in classical mechanics. The virial theorem is an important theorem in celestial mechanics and astrophysics. Particularly, its application is found in case of astrophysics. Uh, the virial theorem is concerned with the time average of various mechanical quantities. It is associated time average of kinetic energy, potential energy, the time average of various mechanical quantities. Also, the virial theorem expresses a conservation law for a system of interacting particles which has already achieved a dynamical equilibrium. In general, the interaction is assumed to be of central force type. So, virial theorem we apply to a system which is moving under central force. The theorem was first given by Earl of Clausius in 1870. Let us consider a system of particles with position vector Ri and applied force Fi for ith particle. A force Fi is acted on a particle whose position vector is Ri. But from Newton's second law, you know that force is equal to dp by dt. So you can write Fi is equal to pi dot. Pi is the momentum of the ith particle. Okay. And let us introduce a quantity lambda. So the lambda is equal to summed over I pi dot ri. We take a quantity lambda summed over I pi dot ri. Now then calculate its total time derivative. Here summation is over all particles of the system. So if we take a derivative dy dt of lambda, so there are two terms. Similarly, we have two terms actually. Derivative of pi dot ri and pi dot derivative of ri. This one pi dot derivative of ri dot plus p derivative of pi, which is pi dot ri. So now the first term, this one pi dot ri dot, if you simplify it, you know pi is momentum mass into velocity mi in ri dot ri dot. So it will be mi ri dot actually mod square, not ri dot same vector dot product of a dot a equal to a square, ri dot mod square. Okay. So which is equal to 2 times the kinetic energy. Kinetic half mv square, it is mv square, so it is 2 times kinetic energy. And the second term pi dot ri is equal to pi dot is equal to fi according to Newton's second law, fi dot ri. So we found d lambda by dt is equal to 2t plus fi dot ri. But now if it is a conservative system, fi is a negative gradient of potential, we can write that. Okay. So before going to that, we take its time average. The time average of equation over time interval tau is obtained by integrating both sides with respect to time t on 0 to time and divided by tau. Anytime, suppose average of f, time average of f means what to do? We take a integration of 0 to t, whatever the time period of tau, f dt, and divided by integration of dt and time period. Whatever the time period, if you take 0 to tau or 0 to pi, 0 to pi by 2, the limit. You know it, this is a formula, so what is actually 1 by tau and integration of 0 to tau f dt Is not it? Hello?
Yes, sir.
So tell me, what is the average of time average of sine theta between the limit 0 to pi? What is the average value of sine theta between the limit 0 to pi? A variable is theta in place of t. So what do you write? It will be, if you write according to formula, 0 to pi, in place of f you write sine theta d theta divided by 0 to pi d theta. This you will know how much?
0.5. Should it be 0.5, sir?
0.5. How? Sine theta derivative is cos theta. Isn't it?
Yes, sir.
Cos, sorry, integration is sine theta is,
Sir, it will be 0.
okay, we'll check it. Sine theta integration is how much?
Minus cos theta.
Minus cos theta, limit put 0 to pi. Okay. And divided by theta, sorry, pi. Theta limit from 0 to pi is equal to pi minus pi. So it will be cos 0 minus cos pi. Cos 0 is how much?
1.
Minus cos pi. You know, I multiply the minus. So minus side, it will actually minus cos pi plus cos 0. And cos 0, so it equal to how much? Cos 0 is equal to
1.
cos pi
-1.
minus 1. So 1 minus minus 1 by pi is how much?
2 by 5.
2 by
2 by 5.
okay, not 0 at all. The average value of cos theta. So any quantity sine theta is this. You can calculate any average quantity knowing this formula. Okay. So now come to the average of each quantity from left hand side and right hand side. So it is so obviously for left hand side I write is equal to integration 0 to tau. Here I take 0 to tau, the limit, d lambda by dt into dt 1 by tau. Here 2. Similarly I take t average, means it contains that expression, and this is the average. So how much is d lambda by dt into dt? You can integration, so it is over lambda only. It is nothing but 1 by tau lambda from 0 to tau, or you can write lambda tau minus lambda 0. So this becomes 1 by tau into lambda t minus lambda 0. Right hand side is 2t average plus fi dot ri average. Clear? Okay.
Yes, sir.
If the motion is periodic, for periodic motion, you know, after time period that same function. Suppose here for a trigonometric function, what is the period?
2 pi.
2 pi. So 2 pi cos 2 pi value same is cos 0. Again it repeats the motion. Similarly, if time period is tau, that means lambda tau is equal to lambda 0. Whatever value you found in 0, it must be equal to the value at your time period. So if the motion is periodic, then all coordinates repeat after a certain time, and tau is this term becomes 0. Okay. If it is not periodic also, we can set it 0 because this period is very large. So a similar conclusion can be reached even if the motion is not periodic, provided that the coordinates and velocity for all particles remain finite, so that there is an upper bound to the lambda. By choosing tau is sufficiently long, the RHS of equation can be made as small as desired even value equal to 0. For non-periodic also we can set it 0. So we make it 0. Okay. So now we can say T average is equal to minus half of average of this quantity. Right? It is actual theorem. So So T average is equal to minus half of Fi dot Ri average. This is known as the virial theorem, and because the right hand side is called the virial of Clausius. This product of this Fi dot Ri is known as virial of Clausius. So it is called virial theorem. But particular case we can use this in place of Fi. We can write if it is the inverse square law of force, and then we can take its exact form. So in general, for a central force, you know, F is negative gradient of potential, conservative force. So we can write Fi as minus del V by del I into Ri cap. Direction is along Ri cap. All central force is directed towards from fixed center. So Ri cap and force is equal to minus del V by del Ri. So if you put here minus del V by del I, Ri cap dot Ri. Ri cap and Ri in the same direction. So this dot product gives you Ri only. So minus del V by del Ri into Ri. So T average becomes half sum of I del V by del Ri. If your system has a single particle, then this sum, we can ignore the sum and the subscript. So R becomes T is equal to half del V by del R. Now tell me what to get for central force motion in inverse law of force for Kepler's problem. For Kepler's problem, our F is equal to inverse square law of force minus K by R square. So what is V? V is equal to
minus K by R.
minus K by R. So use this, what is this form? Del V by del R. So del V by del R is equal to minus K by R square. Isn't it? So V is equal to minus K by R. What is del V by del R?
Minus K by R square.
K by R square.
K by R square. हाँ, it
Minus
will be
cancel हो
positive.
जाएगा ना.
So if you
K by
put
R
K by R square, one R cancel, so it will have K by R. Isn't it? But have minus K by R is V. So it will be what? Minus V average term, average here, but I can write this. Isn't it? It is half K by R, but minus K by R is V. So it is half V average. So for a inverse square law of force, T average is equal to minus half V average. What happens for a simple harmonic oscillator? For simple harmonic oscillator, V is equal to how much? The potential energy? Force is
KR.
minus X, so V is equal to R square.
Minus
Yes,
M
sir.
minus
Force
square.
proportional to R, minus R or minus X. You know it? The force proportional to R, so it will potentially have KR, constant KR square. So if you take its derivative, it will be KR. You know it? KR into R, KR square. So half KR square means V. So for a harmonic oscillator, T average is equal to V average. You also found this relation in your quantum mechanics. For a harmonic oscillator, average value of kinetic energy is equal to average value of potential energy. Here we did do this problem. So for any power law function, V proportional to A r to the power n plus 1, because if A proportional to r to the power n, V proportional to r to the power n plus 1, and del V by del R becomes n plus 1 V, or T bar is equal to n plus 1 by 2 V bar. This is the general Clausius equation or Clausius, virial theorem for any conservative central field. For conservative field, relation T bar is equal to n plus 1 by 2 V bar. So inverse square law of force, what we check already, n is equal to minus 2 here, F r to the power minus 2. So if you put minus 2, you got T bar is equal to minus half V bar. We already got from directly this formula. And for to T bar plus V bar is equal to 0 for Kepler's problem and inverse curl of force. Similarly, calculate for harmonic oscillator is a problem and you found T bar is equal to V bar. Clear? Hello?
Yes, sir. Clear.
Okay. This is allowed theorem. Next we go for Laplace-Runge line vector. Okay. The Laplace. Please, someone is unmuted. Please mute yourself. The Kepler problem is also distinguished by the existence of an additional conserved vector beside the angular momentum. For Kepler's problem, where energy is a conserved quantity, angular momentum is a conserved quantity, aerial velocity is a conserved quantity. Beside these conserved quantities, you have a extra conserved quantity which is a Laplace-Runge line vector. What is its importance? From directly this definition of Laplace-Runge line vector, we can derive Kepler's laws. Okay. For a general central force problem, Newton's second law of motion can be written as F is equal to P dot. So F, since it is a central force, is always directed towards or away from a fixed direct center of force. That means its direction is r cap. We can write r cap as r vector by r vector magnitude r. So it is written as F r into r cap. R cap, write r vector by r. Because a vector is as a magnitude and a direction, and generally r vector is written as a magnitude r and a direction r cap. So r cap will be r vector by r, what is written here. Okay. So now P dot cross j. P in place of P dot you write this F r by r dot j. J angular momentum r cross P. Okay. Now take this cross product. There are three cross products. Fr is a scalar quantity. Fr by r is a scalar quantity, or vector are r, mv. So there is a formula A cross B cross C. What is it called? Now you have a formula A cross
Back minus cap rule.
yeah, B A dot C minus C A dot B. Okay. The formula is B A dot C and
minus C A dot
C
B.
A dot B. Okay. A dot B.
Back cap.
Okay, this is the formula you know. So now use this. Now we have a P is nothing but m r dot velocity. So we take cross product these three. M is a constant. So m, fr and r, they are scalar quantity. They come outside the brackets. Only cross product r cross r. So formula, according to formula, B A dot C, B is r dot is and C A dot B. So C is r dot A dot B. R dot r is r square. So r square r is this. Okay. So now you simplify these quantities. But r dot is equal to how much? A dot, you can check it. We know that is half of derivative of r. Because if you take derivative of r into r, it will become how much? Or r square, derivative of r square 2r dot. If you take it half, it will be r dot. Okay. So r dot is basically r dot from magnitude. Now since j is a constant, for central force problem, angular momentum is a constant quantity. So equation 2, this one can be written as, we can write this as, this left hand side is P dot cross j. Okay. So I can write it, derivative of Pj is how much? We know, if I want to write derivative of P cross j, it will be how much? It will be derivative of A into B, derivative of
P dot
P dot
cross J,
cross
then
j.
derivative of J,
The P cross derivative of J, because since the vector product is not in the order, P cross J dot. But J angular momentum is a constant quantity, so its derivative will be
0.
0. So we drop it. So only d by dt P cross J is equal to P dot J. We have P dot cross J, so we can write in place of that derivative of P cross J. So now derivative of P cross J is equal to M FR by R all into R dot, because this one is R dot, calculate minus R square R dot. Okay. Now slightly rearrange these quantities. For that, I take this R to inside it and multiplied and divided R. That means it will become shape R and here R square. So if I take it to this, we become M R again. I take R from here common, so actually it becomes same FR R square. R square I divided this and take R common. Okay. So here also R square. I divided R square. So this R square cancel here from R square. Remain there is a 1 R, cancel 1 R. But again taking R from each term, we have a this form. R square here, R square minus R. Okay. So now derivative of P cross J becomes minus M FR R square, and this term, this is not but derivative of R vector by R. V derivative of U minus U derivative of V by V square, if take derivative of this quantity. So but for Kepler's problem, FR is minus K by R square. Putting that, we found R square cancel, minus plus. So mk d by dt P cross J is equal to mk d by dt R vector by R. So mk scalar quantity, I can take it inside the bracket. So our d by dt P cross J become d by dt mk R by R. And taking one side, d by dt P cross J minus d by dt mk R is equal to 0. That means derivative of a quantity P cross J minus mk R by R is 0. P cross J minus mk R by R is a conserved quantity, and that is known as Laplace-Runge length vector A. So A is known as Laplace-Runge length vector. Since J is perpendicular to P cross J and R is perpendicular to J, then A dot J is 0. Okay. Here A is perpendicular to P cross J. J is perpendicular to this P cross J. A is along the direction of P cross J. You know it. But if you compare it, P cross J, it is perpendicular to both P and J. So J, again J is equal to R cross P. J is perpendicular to both R and P. A is perpendicular to P and J. J is perpendicular to R and P. That means what can I do? J is perpendicular to P. A is perpendicular to P and J. If you imagine a situation, J generally is perpendicular to P. Suppose this is P, perpendicular.
They are all mutually perpendicular, sir.
Yes. And A is perpendicular to both P and J. Obviously, if you take the axis, then it is X, Y, so it will be Z. A is perpendicular to both. So A dot J is equal to 0. A is perpendicular to B, so J, so A dot J is 0. It follows from the orthogonality of A to J that A must be some fixed vector in a plane of the orbit. If theta with the angle between R and A, then we can calculate A dot R is equal to AR cos theta, but A is equal to P cross J minus MKR by R. You put the value of A here. So A dot J means, A dot R means P cross J dot R minus MKR by, if this term at the left hand side, okay. A dot R is equal to in place of A, you write P cross J minus MKR by R and dot R. But this equal to AR cos theta and this equal to A cross B dot C is equal to, or A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. You know another vector identity. A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. Isn't it? B dot C cross A. You know it? Or? A cross B. Hello? This is a vector identity or not?
Yes, sir.
A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. Here we have a form, say, P, the dot product is, you know, commutative, so A dot B is equal to B dot A. Here is a form P cross J dot R. Suppose this one. Alternative A cross B dot C. So we can write this as R dot P cross J. Okay. This term dot with, suppose, A cross B first term and R dot B cross C. Here only change the dot product is commutative. Okay. Then we use the second vector identity. First, in the first step we take dot product is commutative. So A dot B is equal to B dot A. Like this. In the second step with this identity, R dot P cross J means A dot B cross C is equal to B dot C cross A or C dot A cross B. A dot B cross C, you take C dot A cross B. C is J, C dot R cross B. Clear? But R cross B is J, so J dot J is equal to J square. Finally, we found A R cos theta is equal to J square minus MKR. So A cos theta will be J square by R minus MK, dividing R with each term. So J square by R is equal to A cos theta plus MK, or 1 by R, what you got in the Kepler's first law, A cos theta plus MK by J square, or 1 by R taking MK by J square common, will write 1 plus A by MK cos theta. Isn't it? So it is a general form with eccentricity. If you compare the general, the Laplace transform to another way to derive the Kepler's problem. This type of equation we got in Kepler's first law. So in comparing the orbit of Kepler's problem, we have 1 by R is equal to MK J square 1 plus E cos theta is eccentricity. So eccentricity is here A by MK, or A is equal to MKE. But in Kepler's problem, we found eccentricity 1 plus 2 is J square by MK square. So comparing with this equation, you can say A is equal to MK square root of 1 plus 2 is J square by MK square, or A square is equal to M square K square plus 2M is J square. Thus for Kepler's problem, we have two vector constant of motion J and A and a scalar E. So J is a angular momentum conserved quantity, energy is a conserved quantity, and here we get another Laplace transform vector is a conserved quantity. Okay. So these are things. Okay, clear?
Yes, sir.
Okay. Then we go to the small oscillation part. Small oscillation. Small means here amplitude of oscillation is very small. So small amplitude, this one is very small. Stable and unstable equilibrium. We know that at equilibrium, total force acting on the system is zero. But there are two kinds of equilibrium, unstable and unstable. These are two given, one stable and one unstable. Okay, so an equilibrium position is classified as stable equilibrium if small disturbance of the system from equilibrium results only in small bounded motion about the rest position. If we slightly disturb it, it will execute a simpler motion or a motion and about equilibrium position. But if you slightly disturb it, it fell down. Okay, you see. Okay. Suppose a paperweight, when you slide move it, execute a motion straight. Suppose you are putting a egg like this and slide disturb it, then it will break down. Similar the thing. For the unstable equilibrium, if slightly disturbance produce unbounded motion, motion breaks. For example, if you are putting an egg on a table with one end slightly, if slight disturb, it will break down. Or if you put a stone here in some place like this type of thing, top, then you slightly disturb it, it will fall down. Okay, this is an unstable equilibrium. So how we mathematically know that example at rest, a pendulum at rest is a stable equilibrium, but the egg standing on one end is unstable equilibrium. Okay. But in both the case, okay, since force is zero, what about potential is a constant quantity? The force is derivative del v by del x. So at equilibrium force is zero. How you know? Del v by del x is equal to zero. Force is del v by del x. So that is V is either stationary quantity, maybe maximum or maybe minimum. So if V is minimum, we call it is a stable equilibrium case, and V is maximum, we call it is a unstable equilibrium. For minimum, how to check a quantity minimum or not? In mathematics, we use the second derivative. If del square V by del x square greater than 0, then we call it V is minimum. If del square V by del x square less than 0, we call it V is maximum. V maximum means unstable, V minimum means stable equilibrium. Clear? There are two figures for maximum and minimum regulation. So how you calculate? If a potential is given, you have to first check at equilibrium point. How you check? Hello? Okay, I have given some problem in the last. Suppose this is the system. A potential is given. How you check it is its equilibrium point? At equilibrium, what happens? At equilibrium, force is equal to? Hello?
Zero, zero.
Zero.
Zero, sir.
So force, how you calculate force from potential?
Dou v by dou x.
Del v by del x. So it will be zero, not it. So if you multiply both sides minus, so minus 0, 0. So V is given. So you have to calculate del V by del x. Here del V by del x is how much? 2ax minus
B by x cube. 1 by 2 B by x cube.
minus 2. Minus 2. 1 by 2. This one?
3 it should be.
And derivative. Derivative 2x. Here
Yes,
derivative.
Yes, sir. Yes, sir.
Minus 2 b by x cube.
Yes.
This should be 0. So this is, so what is the value of x? That is actually your equilibrium point. From this solution, you x is how much? You found x4 or 2 cancel ax. If 2 take common and divide, then we found ax is equal to b by x cube.
X cube.
So that x4 is equal to how much? B by
A.
So x square is equal to plus minus b by
Square root. Root of 1.
and x is equal to the power 1 by 4. These are the equilibrium point. Or you can write ax is equal to b by a to the power 1 by 4. So these are the equilibrium point. Next, you check it is stable equilibrium point or unstable equilibrium point. What you do with second derivative? So second derivative of this quantity is how much? 2x minus 2b by x cube. It will be 2a
Plus 6
plus 6
B by x to the power
4.
4.
So this will be this is the derivative. We have to check it is greater than 0 or less than 0?
It's greater than 0, sir.
Greater than 0. So greater than 0 means it is minimum. V is minimum, is a stable equilibrium case. So these points are the stable equilibrium points. Clear?
Yes, sir.
Similarly for this, tell me what is the stable equilibrium point? Potential is given. So first calculate the equilibrium point. F is equal to 0. Take its derivative. It is how much? If you take derivative uv, first to find u into derivative of v plus v into derivative u 2x by 2. Isn't it? Is equal to 0. Derivative how much? Derivative u into v plus u into derivative of v. So that it is simple. X minus 2 you can take common because x minus 2 in each term. So if x minus 2 take common, it will be again x minus 2 plus 2x is equal to 0. Hello?
X
What is the
minus
value of
2,
x? X value is
x minus 2 into 3x minus 2.
so what is the value of x?
x ଗୋଟେ value ହେଉଛି 2 ଆଉ ଗୋଟେ ହେଉଛି 2 by 3.
So x have two value. One is 2, another is
Another 2 by 3.
3.
2 by 3.
These are the equilibrium point value. Now check which one is stable equilibrium, which one is unstable equilibrium.
X equal to 2 to stable equilibrium and x equal to 2 by 3 to unstable equilibrium.
Take the second derivative. So if second derivative means 2x minus 2 and this function, here you can take this quantity, this. So take the second derivative, x minus 2 into the derivative 3 plus the derivative is 1 into 3x minus 2. So this is actually 6x and 3 into how much? Minus 6 minus 2.
Minus 2.
Minus 8.
Minus 8.
6x minus 8. Put x is equal to 2. So it will be, for x is equal to 2, 6 into 12 minus 8 is positive.
4. Positive.
For x is equal to 2 by 3.
Negative.
Minus 4.
Minus 4 negative. So which point is the maximum, minimum? This is minimum. It is maximum. It is stable equilibrium. It is unstable equilibrium. The stable equilibrium is x is equal to 2. So body executes simple harmonic motion, a small oscillation about its stable equilibrium point, not unstable equilibrium point. So body executes oscillation about its stable equilibrium point. Okay. Now, go for the formulation of the problem. Actually, small oscillation. For a conservative system, potential energy is a function of position coordinates only. We know that for a conservative system, we potential is a function of position coordinate only. Again, for equilibrium condition, we have the generalized force is equal to negative gradient of potential Q. Here, F in place of F, I generalize to Qi. Qi equal minus del V by del Q 0, and at equilibrium, the force is equal to 0. That means del V by del Q is equal to 0. So the potential energy therefore has the extremum value at the equilibrium configuration. There may be number of equilibrium points. Let us consider the case of stable equilibrium. Okay. Since here the departure from equilibrium was very small, all function may be expanded in Taylor series. So if you slightly disturb it, then execute simple harmonic motion. Then slightly change, so we can expand it. The change is very small through Taylor series expansion. Let that change is eta I. So Taylor series expansion. This is for equilibrium configuration here. If there is Q0i, Qi is equal to Q0i plus small change eta I. Okay. Now the eta I are generalized coordinate and expanding the potential in terms of Taylor series. You know, according to Taylor series expansion, the function is function and derivative about the equilibrium point into the variable. The form of Taylor series expansion, you know that. Okay. F, the Taylor series expansion f x plus x0 is equal to how much? Right. If x0 is the equilibrium point, f x0, sorry, x0 plus h, yeah, we can write
F,
it.
F dash x0
Uh,
into
f x0 plus del f by del x at x equal to x0 into x minus x0 or h. You write it h into del f by del x at equal to 0 plus h square by 2 factorial del square f by del x at x is equal to x0. Okay, formula is like this. You know that. Okay. Del square of 0. But at equilibrium position, we know that del v by del q 0 is 0. This term is 0. So we have only two terms. Again, the first term, neglect higher term, only keep two terms. Again, the first term in the RHS is the potential energy of the equilibrium position, and by shifting the arbitrary zero potential to constant equilibrium, it is a potential constant equilibrium potential plus this. Now, let us set this potential equilibrium potential is 0. You can set it. So, our now V is equal to this term. V is the only sum over half I j del square V del q del q j eta I eta j. And this quantity we write as matrix from Vij into eta I eta j. Vij means del square V by del q j depends on the equilibrium point. Similarly, we know that kinetic energy is equal to half mv square, or if there are number of particles, we can write like this: half sum over ij mij q dot means q1 dot q2 dot qi dot qj dot. Here we similar form, you can, but qi is equal to q0i plus eta I. Q0 is a constant value, its derivative will be 0. But we take, so qi dot means only eta I dot, and derivative is 0. So kinetic energy can be written like this also. So potential energy is same, half Vij, here can half Mij. Or half Mij, or for generalization, we can tell Tij. Like Vij, here V, Vij. Here T, so we will call it Tij. And Vij and Tij are symmetric. If you change Ji, it does not change. It will Qj or del Qi. Similarly, Mj, Mj. Symmetry or change of Ij. Tij is equal to Ji, Vij, Vji. So the Lagrangian becomes T minus B half sum over Ij, Tij eta I dot eta j minus Bij eta I eta j. If the Lagrangian, what is the Lagrange equation? Using this d by dt del L by del eta I dot minus del L by del eta I, you got the Lagrange equation Tij eta I double dot plus Bij eta j is equal to 0. From this Lagrangian, you can got this equation. Eta here is a summation, sum. For each I, we have this equation. N equations. So, but that is only summation of j. For each I, we have equation. Equation of motion are linear differential equation. And how you solve it? You know, it is like a double derivative. And d square y by dx square in term plus let's say a y or a d square dxy plus by is equal to 0. This is the equation. How you solve it? Second order differential equation. You can solve it using auxiliary equation m, and generally everything in our physics mostly all are owing this type of equation. Starting from simple harmonic oscillator, we take it solution will be something e to the power minus sin theta cos theta, or in combining you can say e to the minus I theta or I plus I theta, e to the power I something. So let the, for this, since there is a plus symbol, you have to take it minus here. So it has a solution of this equation is this. By using this here, you can get the exact equation. Okay. So C A J e to the minus omega is the angular frequency. You know from this expression. So now in terms of this angular frequency, putting this here, we found Vij minus Aj minus omega square Tij Aj is equal to 0. This is 0 means Aj is multiplied here, we take it common. So Vij minus omega square Tij multiplied with the vector Aj is always 0. This implies that V minus omega square T, Vij and Tij are component of this V and T tensor, must be always 0. Okay, that means depending on the Ij dimension, we have number of angular frequency. For one dimension, only simple equation V minus omega square T is equal to 0. If dimension increases, 2 dimension, 3 dimension, we have this type of determinant. Okay, a root of this equation is your angular frequency. Our generally question asks for a one dimensional problem, but for one dimensional problem, let's say one dimensional simple harmonic oscillator. A simple harmonic motion, kinetic energy is half mx dot square, potential energy is half kx square. That means comparing with these two equations, Tij is equal to Tij half Tij eta eta dot, Vij is equal to half Vij eta eta j. If you compare these two equations, we found Tij Vij is equal to k, Tij is equal to m. That is one dimension, so there is no ij. Okay, V is equal to k and T is equal to m. So the equation V minus omega square T0 gives k minus omega square 0, or omega is equal to k by m root over. But V is equal to, how you got the V? Vij, your formula, del square V by del x square. Del square V by del x square. Q del Qj, it is same. So V is equal to del square V by del x square at 0. So omega angular frequency is del square V by del x square at x is 0 by m root over. This time of question, then I'll ask calculate the angular frequency and a system of potential is given. So we take is second derivative and divide m. Like here two problems what we do here, actual question is find the angular frequency of small oscillation about the minimum of the potential. A particle of unit mass means m is equal to 1. So according to your formula, omega is equal to square root of del square V by del x square at x is equal to x0 means 0 means a stable
equal
equilibrium
to
point. This is the formula. Here m is equal to 1, only del square by del v square v by del x square at x equal to x0. We found the stable equilibrium point is this one. V by x for v, or x equal to v by 4 to the power 1 by 4. So del square by del x is this one. Put x equal to x0. Then v by a to the power exponential v by a. If you put here v by a, so it will be how much? V cancel 2a plus 6a, so it's equal to 8a. 8a, so omega is equal to 8a root over. M is equal to 1, so omega is equal to 8a root over of 8a. Okay, so tell me here, what is the value of time period of oscillation? The time period of oscillation means t. We calculate t is equal to 2 pi by omega. Calculate omega then t. What the value of omega? Here stable equilibrium point is x is equal to 2. And del square v by del x square already calculated 6 minus 8. So what is omega? Using formula, or here also given also unit mass. So m is equal to 1.
6x minus 8.
Omega equal to 2.
2. Del square del v x square at x is equal to 2. Root over. So we already put 2, put 12 minus 4. Oh yes, 4 root over is 2. Omega is equal to 2. So what is t? T is equal to
Pi.
pi. Okay. You can also do other examples. Take one example. It is a triatomic molecule. Generally, in triatomic molecule case, there are 3 molecules connected like this. Suppose H2O or anything other molecule. HH. So there is in middle one massive atom, and in the two ends there are two less massive atoms. So for this, what is the potential energy if you take this distance x1, x2, and this at equilibrium separation b, and then coordinate will be x2 minus x1 minus b, and here the difference will be x3 minus x2 minus b. Half kx square for they are just like a simple harmonic oscillator connected by spring. So half kx plus you write this. Okay. And using the coordinate eta I, we have observe all things. So it is in terms of eta I. Actually, potential energy half kx square means eta 2 minus eta 1 square, and eta 3 minus eta 2 square. This is the potential energy of the system. So opening this whole square bracket, you found this. So hence we can construct the V tensor. The tensor whose components are Vij and Tij, they are actually tensors. Whose component V and T are tensors. This component of the tensor are Vij and Tij. So how you construct this temperature by seeing the potential? We write this in a form of matrix. So this is one component. Eta 1 square means eta 1, eta 1. So what is the component here with eta 1 and eta 1? It is your 1 component. Our form is half Vij. So and eta 1, eta j. This is the form half Vij, eta j. So half cancel. So eta 1 square. So here rest is k. So V1 point k. Okay, so see the diagonal points first, then 2. Eta 2. This component 2 component. Here component coefficient is 2k. For 3. Eta 3 square component is only k. Now go to the product term. And 2 eta 1 eta 2. Coefficient is 2. But it may be eta 1 eta 2 or eta 2 eta 1. So when we, for small oscillation case, when we write the components, if there is product term, we give equal credit to each term. Means it may be a term of 1 2 or 2 1. Since there is a symmetric, Vij is symmetric, 1 2 term is equal to 2 1 term. So we give half to 1 2 term and half to 2 1 term. Suppose here coefficient is 2k, we give minus 2k, minus k to 1 2 and minus k to 2 1. Similarly here coefficient is minus 2k, so we get minus k to 2 3 and minus k to 3 2. But there is no 1 3 term, eta 1 eta 3 coefficient, that means 0. So 1 3 0 3 1 0. Clear?
Yes, sir.
So, kinetic energy is say half m1 eta 1 dot square, half m2, half m3 eta 3 dot square. The mass is same. We can write this: half m eta 1 dot square, half m eta 3 dot square, half capital M eta 2 dot square. What is this coefficient? Generally, kinetic energy is diagonal. most of this. So here m small m is coefficient is half Tij eta I dot eta j dot, half Tij eta I dot eta j dot. So you compare, a coefficient is m and capital M and same. And then v minus omega square t determinant is 0, and then get the solution for omega. We found solving this omega value will be these three. Okay, these are the frequencies. Okay. Next is another part, eigen. This is the eigen value omega, eigen functions. How we calculate the Lagrangian of a system? You know, t minus v. This one, and Lagrange equation. We got this equation. This is the solution. We got this in the last slide. Next we go over. So these are the, we know this is the solution and the secular equation. Root of this equation gives you different value of angular frequency, and each value we give one mode oscillation known as normal mode. For each value we have one mode of oscillation called normal mode. So these frequencies is known as normal frequency. But we have to calculate exactly what are the normal mode or normal coordinates. Omega is called normal frequency, and for normal coordinates we have to say like that. Let us assume the J1, J2, J3 are the normal coordinates. Since it is a simple harmonic oscillation, so J1 obeys this relation where frequency is omega 1, J2 obeys the relation where frequency is omega 2, and similarly Jn obeys the equation where frequency is omega n. This new set of coordinates J are related to our old set eta j by some transformation equation as jk, jk, or in explicit form we can write like this. So we set a normal coordinates so that which satisfies the equation of simple harmonic motion with each omega as the frequency, and this relation between eta j and jk can be done through a transformation like this. Next aim is to find this matrix or component a11, a12. If you exactly know this, then we can, from eta 1 we can construct J1. Okay. For this matrix capital A, the matrix called capital A, which obeys two relation, A transpose T A is equal to I. T is kinetic energy. A transpose T A is equal to identity matrix, and A transpose V A is a lambda, which is a diagonal matrix. So particularly we use this one to get the exact one. A T T A is equal to identity matrix. So for normal coordinate, our secular equation, this one we got its root. So if you multiply it with all A, and it will be multiplied with all A, so that there is a something, let's say multiplied with this. How matrix multiplication? Each row is multiplied with each column. Isn't it? So first row, whatever is multiplied with column, second row column. So in this one, so let's say this is a column given 1k, 2k, for k multiplication. We get the multiplication one, and then we use the identity one to get the exact components. We take an example for that. Let us consider the parallel pendulum. Pendulum, what given in our syllabus. To pendulum. What a double pendulum, two pendulum. This is two pendulum system. Two pendulum system, two coordinate theta 1 and theta 2. The pendulum are connected by a spring of spring constant k. So you can solve it. The first pendulum kinetic energy will be a simple pendulum. Half m L square theta 1 dot square. Potential is MGL 1 minus cos theta. And here for we have theta. Here for theta 1 we get one pendulum, theta 2 another pendulum. Okay. Theta 2 same expression. This. So due to the extra, the spring has a potential energy, you know, due to spring, it behaves a simple harmonic oscillator, half k x square. X square means distance is x2 minus x1. So it will be x2 minus x1 square. So if you convert the kinetic energy in terms of x, y, z, we got this. Okay. Kinetic energy this one half m L square theta 1 dot square plus theta 2 dot square. Potential energy this one we got. Now simplifying it and writing the tensor T is equal to this, so Tij is equal to ml square 0 ml square. From this we got this because ml square is the coefficient with theta 1 dot theta 2 dot of diagonal 0. Your potential what is multiplied with theta 1 mgl plus kl square theta 2 square, so you can got that. Okay, think you can set this Vij mgl comparing the coefficient Vgl plus kl square Vgl. Okay, from here you can coefficient of theta 1 square is 1 component, theta 2 square is 2 component. Theta 1 theta 2 means it will be half. Half goes to theta 1 theta 2, half goes to theta 2 theta 1. And kl minus kl square goes to this and this. Clear? Hello?
Sir.
Yes, sir.
This is important. Huh? So you got v minus omega square t this, and this root will be give you on the angular frequency, normal frequency of oscillation. Okay, again how you get this normal modes or normal coordinates, this will obey beta 1 eta 2, the coordinates they obey this relation. What do you see? And they related with theta j as j k eta k. So theta 1 theta 2 will be a1 a2 in the explicit form. And for each omega, let's say for omega is equal to omega 1, we have for a1 vector. That means a1 vector means we will multiply this component for omega 1. And this component we multiply with omega matrix omega v minus omega square t to get omega 2. Okay, this is even. This is v minus omega square t matrix. We multiply with first column to get the omega 1 value. So putting omega 1 square g1, we found value of a1. We got a11 is equal to a21 from this equation. Two components are same, 1 equal to 1. Again for omega 2 case, we get a12 a22 multiply a12 a2 second column a12 a22. From that we get a12 is equal to minus a22 beta. Two are same, two are alpha beta, alpha minus beta. But how you get the alpha beta value? Use the condition ATTA is equal to identity. ATTA identity means you can tell a diagonal element 1 1 of diagonal 0. You found the exact value of alpha and beta. We found alpha is alpha is equal to 1 by 2 is beta. So we got the exactly A matrix and obviously theta 1 theta 2. Clear? The mathematical details given here you can easily understand. Another problem is your double pendulum. It is double pendulum means one pendulum is attached to another pendulum. Okay. So this like structure. So here two x component and y component. So x, this is x value. This is x value of m2, and this is y value of m1, and hold y value of l2. So you can say y1. This is how much? If this is the L1, the distance will be
Cos
L1
theta.
minus L1 cos theta 1. Okay. Then it will reach to this position. Similarly, y2 is equal to this plus this R2 L1 minus cos theta plus L2 minus L2. But you did in the simple pendulum, you also use these formulas here. Right. Then x is equal to L1 sin theta 1, x this value. Will be L1 sin theta 1, and here L2 sin theta 2, so L1 sin theta 1 plus L2 sin theta 2. So kinetic energy half m dot y dot square, half m2 x2 dot y dot square. We found a value, and potential energy, so we set Tij, and similarly Vij, omega b minus omega square t is equal to 0. You get, and from that you got the value of omega square, angular frequency. There are two also. There are two cases here are given complicated one. Generally, m1 is equal to m2 you can calculate. For m1 is equal to m2, L1 into L, we have the frequency this one. Other thing is complicated frequency. Okay. But this is a small oscillation. So we have. So here, tell me what is the T tensor component of T tensor, and what is the component of V tensor? What are the component of T tensor? T is equal to how much? Hello? This is your T, S dot square, and this is your V. Isn't it? So what is the T tensor? First component of T tensor is how much?
Half.
By 2.
Half. In T we have half Tij, eta I dot, eta j dot. Half is already in the definition, so you don't
M 0 M
M is
0 M 0
0 M how much? There 2m2 dot square.
2
How you get 2? But multiplied with half.
4
So it will 4m. Yeah.
4 M.
So what V? Tell me. For V. Similarly, half Bij, eta j. So if half is 5 by
8.
2, half is already here, na? 5 by 2k. Here, this one, minus 2k. So if you take half common, it will be minus 4. So it will be minus 2k. I have to take half common. So if half common, it will be 5 by 2. It will be 4. It will be 4. So then, okay. So if product term will be divided 2, so it is minus 2k, and here 4k. Then you take for frequency V minus omega square T, determinant is equal to 0. Putting 0, you got the value of omega. Okay, you do this problem. Okay, one thing is open. Another last unit is actually force oscillation. It is in lost force oscillation resonance thing. Why they include in MSc? I don't understand. I give you this note and you read that. A very simple resonance and force oscillation. Okay, on this material you can read this. Okay, so your paper 002 is completed. The next class we discuss about 006. Okay.
Yes, sir.
Are any doubt?
Yes, sir.
Yes, sir.
Okay.
Sir, please put on the PDF to the official group.
Okay. Yes, sir.
Thank you, sir.
Thank you, sir.
Any question?
Sir, for the beginner, what should be the approach to understand the intricacies of classical mechanics 1 and advanced 1? What is your suggestions?
Classical mechanics is the first subject for physics. You can
Yes, sir.
say.
Yes, sir. Yes, sir.
Uh-huh.
Anything to be done beforehand, because I think knowledge, prior knowledge of basic physics and
Basic
mathematics and
Newtonian mechanics, no other things we are using.
yeah.
Basic Newtonian mechanics, if you know, then you can study the classical mechanics.
What is it?
Actually, my next class is which day? Monday, Tuesday, 27, 28. I may be slightly take it before or after. Okay. They will inform you if I change the time. I told them. Besides 4 p.m. and 5 p.m., your classes are done at 9 and 10. Hello? So what is your class time?
Sir, in normal day, 4 p.m. to 6 p.m. Or but in holiday, in the morning, 9 to 11 a.m.
Holiday
And
night.
also 4 p.m. to 6 p.m. Holiday means Saturday and Sunday, sir.
Okay. Okay.
सर एग्जाम में जो क्वेश्चन आएगा वो प्रॉब्लम बेस्ड आएगा या डेरिवेटिव?
वो मुझे पता नहीं है, वो एग्जाम पैटर्न कुछ मुझे पता नहीं है। वो लोग बोलेंगे क्या, वो कैसे एग्जाम करेंगे।
यूजुअल सर, यूजुअल पीजी प्रोसेस में बहुत आते हैं सर, बहुत यूजुअल पीजी।
40% ऑब्जेक्टिव, 60% सब्जेक्टिव।
ओके, थैंक यू सर।
ओके, मैं लीव नाउ?
Yes sir.
Yes, sir. Thank you so much.
Thank you sir.
Thank you, sir. Thank you, sir. Thank you, sir.
40% ऑब्जेक्टिव, 60% सब्जेक्टिव, यही बोला ना
हाँ
सर? क्वेश्चन पैटर्न क्या बोला? 40% ऑब्जेक्टिव, 60% सब्जेक्टिव।
नहीं सर ऐसे कुछ नहीं तो बोले।
हाँ।
सही तो बोले, बताए। दैट इज आई कैनॉट। आप लोग कैसे प्रिपरेशन कर रहे हैं सब?
सर आपको हम बाद में टच करेंगे, हाँ, नॉक करेंगे।
बिल्कुल बिल्कुल बिल्कुल,
ठीक है।
ये 18th मॉर्निंग वाला क्लास हुआ क्या क्वांटम मैकेनिक्स का?
हाँ, मॉर्निंग में हो रहा है सैटरडे और संडे को।
अच्छा।